Amber Lab at Caltech. Today I'm going to talk about using a simple hybrid linear inverted pendulum model to generate a continuous walking and stabilization for the robot Cassie. So we typically model walking as a hybrid dynamical system. A lot of people talk about this today. So I'm not going to in detail. So basically you can model walking as different domain and with impact and switching surfaces. And for the control synthesis, we typically model we're working as a periodical solution to the hybrid system, and optimization is used as a tool to find the periodical solutions. And when it's a highly non-convex optimization, but it's still solvable. If you get the solution, you can extract the features from the solutions, such as leg length, angle, pelvis orientations, and to be the desired behavior you want, and the control would be driving the actual behavior of the system to the desired behavior. Zero needs outputs y. So if you do that right, and if you are lucky, you can get working, and but that not always happens because there is always under actuation, right? So when you are robot doing this kind of heel to toe working, it is underactuated about the foot ruling. And if you have a robot which have very small feet, for example, Cassie have no actuation about the toe rule, so that is also underactuated. For this kind of behavior, you can decouple the continuous dynamics into two parts, right? The first one would be the control dynamics, where the input U, the torque, appears, and the second part would be the underactuated dynamics. The typical one canonical way to solve this problem is to construct a hybrid zero dynamic surface y, where y is driven to the desired behavior, and you use optimization to construct that surface, and you are trying to find a stable orbit on that surface. So when your outputs are driven to the desired, the underactuated dynamics is the zero dynamics. And the way you do that is to make sure this is stable by solving the right y. But this is a pitfall, right? If your robot model is not accurate, or you have disturbances, this can lead behaviors you don't want. You don't want to track a trajectory that you don't even have input into the system, right? So one example is a backflip of the Atlas robot, right? When it does the backflip, the zero dynamics is the whole body rotation, right? The whole body pitch. And if we want that to behave along a pre-planned trajectory, that's not going to happen most of the time. So how do we mitigate the unstable zero dynamics? You can think about doing replan, right? And that's more like a MPC approach. And so far, that's not computationally feasible. And you can think about the pre-plan, right? You build all the discrete behaviors ahead of time, but the issue is you don't understand the transition very well for the zero dynamics. So the approach like I will pose, and also most people are thinking of right now, is to approximating the underactuated dynamics, with some kind of model for faster planning. And if we look at all the falls from the DARPA robotics challenge, right, we intuitively understand the zero dynamics, right, which is a forward position velocity, is behaving like some kind of pendulum dynamics, right, and plus some a bunch of stuff. And let me see if I can. Let me just stop the video so you can listen to me. So basically, the bunch of stuff is going to have all the outputs y right there. So when you want to use this kind of approximation, right, you want the y a bunch of stuff don't behave too don't kill the pendulum dynamics. You want the y to behave properly, right? So for example, you don't want the center mass to oscillate too much, right? That's not going to happen, and you don't swing the back and forth that will having the swing like inertia dynamics, kicking in the zero dynamics. So the model I approach is a hybrid linear inverted pendulum model. It has double two domains, single support and double support. So for the single support, I assume it's a linear inverted pendulum dynamics without ankle actuation. And for double support, I just assume there's a constant velocity. And I assume the velocity doesn't have jumps between the switching, and there is only position switching based on the step length you select. So I also assume the duration of each domain are fixed. Here is an example of the walking. So for this simple system, I want to characterize what are the orbits, right? The first orbits I care is where the system states are behaving on the same orbit with two legs as the support legs. So this theorem is saying that for all the period 1 orbits, P1 orbits, the initial state and the final state will be on these two yellow lines. And here I'm showing 3 different orbits. And for each orbit, you can find the step length in this formula. So here are 2 examples. For example, the left one is the blue orbit, and the right one is a red orbit. So for each orbit, it has its own desired velocity. Given a desired velocity, you will find a unique P1 orbit. And you can imagine the green one will be walking backwards, right? And there is another orbit I care because you have 2 legs, right? So there is another P2 orbit, which the system states are evolving on different parts of the orbit as 2 legs as a support respectively. So this theorem is very similar to the first one. For P, this is saying like the initial states and final states are on these 2 yellow lines. I'm showing 2 sets of yellow lines, right? And there is an offset from the origin, the D2, which is determined from your desired net velocity. So again, I'm also showing 3 orbits here, and here are 2 animations of the walking. So for the left one, it's a gray one, right? And for P2 orbits, given a desired net velocity, there is not a unique orbit. Actually, there are infinite number of orbits you can create. And the red one is a red one, right? It has non-zero net velocity as is shifting upwards. For this, so the message here is all the orbits are connected, right? And that's a nice thing. You have a continuity here. So for this simple system, we can find the closed form stepping controllers because there is no anchor actuation here. So the only way to stabilize the system is changing the step length. This theorem is saying that given the P1 orbit, I can use this step controller based on the velocity feedback, and I can find the range of the gains and also the optimum ones. The optimum ones can stabilize the velocity within 1 step and the position by 2 steps. So for P2 orbits, there is a very similar theorem. The only difference is there is a negative sign on the gains, and you have a different target velocity at the boundary state based on your support legs. Right. So the short message here is all the orbits can be stabilized globally, which is also a nice thing. Right? So we want to first try to use this kind of stepping controller on a similar approximated dynamics system, which shows the actuated spring-loaded inverted pendulum model. This is a sleep model with actuation. The actuation is changing the leg length, which is in theory of the springs. And the reason we can think about using is, for example, looking at the dynamics in the single support. It's exactly a pendulum, linear inverted pendulum dynamics plus some remainder term. And we want to create a behavior that behaves like the linear inverted pendulum model I proposed, right? So the behavior is having this kind of periodical behavior. So I use trajectory optimization to generate a lag oscillation. This is step in place, and this corresponds to the origin in the linear inverted pendulum state space, right? And I can use the stepping controller, which is a closed form, right? There is nothing to tune, and to steer the system to any velocity I want, as long as it is feasible, the step length is limited. So on the right, it's a trajectory of the position and the velocity, and we can show it. We can say it is very close to the one of the linear inverted pendulum. And here is a similar, the same one for P2 orbits, and it's not exact because the dynamics is not exact, right? But it's close, and we can get periodic behavior. So for 3D under actually working because we have 2 planes, right? And we can have 4 kind of composition of this P1 and P2 orbits in different domain. And for example, this human walking here is like a P1 in cyclic plane and P2 in coronal plane. So for using it on chassis, there's additional not important outputs, like you want the parallels to be fixed, swing leg orientation to be fixed, right? This assemble them, we will get all the outputs we need, and I don't have too much time to talk about the details, but we use CRF-QP for controlling the outputs. So here is one simulation result to driving the robot from static configuration to a stepping place gate, and then we steer the robot to a desired velocity afterwards. And you can see the system behaves closely to the orbit of the linear inverted pendulum model, but it's not that, but it converges. So here, I can steer the robot to different directional velocities. For the one you saw, it's walking forward, and on the left upper corner, it's walking to the side. And for this lower left corner, it's walking in diagonal directions. And for the right one, bottom corner, it's walking backwards. So we can, okay, let me go back. So we can implement the four realizations of the walking, right, based on the composition of the P2 and the P1 orbit. So this is for realization for a given desired velocity. That is P1, P1, but that is feasible, physically not feasible because the kinematic constraints are violated. But for the other three, it's okay. So you can walk in different fashions to go to a desired velocity, having the fixed stacking frequency. So just quickly conclude, I have a hybrid linear inverted pendulum model for orbit characterization and stabilization. And the closed form stepping controller can continuously generate different walking behaviors, right, for 3D under-actuated walking. So quickly, the future work, one is the experimental implementation. And we can also think about this kind of simple model-based fast planning for periodical hopping. Right? This is a single hopping behavior, but we can try to do periodical ones. And we can also think about using this simple model to do fast planning to get to do path following. And there is also the transverse motion, which is a yaw. I didn't consider, but that can be also decoupled. Okay, with that, I will take questions there.
Questions?
Peter. Peter at the University of Wisconsin. Could you talk more about your very last point? How you want to get it to actually steer with yaw?
I haven't worked on that, but I have some intuition.
Yeah.
So it's basically like the concept of decoupling, right? The dynamics can be decoupled, and with some remainder term, you can look at each dimension like a respective, right? And the theoretical guarantee, you can think about that. It's more like input state. And you can just plan individually on each dimension and then compose them. It's like exactly what I did, planning the sagittal and the lateral plane and then compose them.
But it seems like it's you don't, if you're just using foot placement, you don't have this any more freedom, right? So
okay, I see.
it seems like it'll interfere, right?
So I'm not doing foot placement for the yaw, obviously, because you're not going to get that. So there's yaw at the hip for the robot. So that's where you plan that motion. So you don't place the foot to the yaw. You use that hip yaw to do the yaw. Basically, okay.
Excellent. Yeah, Joey from the University of Washington. I was wondering the gains that you showed for the P1 and P2 orbits. You showed theorem for coordinate solutions for optimal gains. What cost are those optimal with respect to?
So how fast you can stabilize it to the desired velocity?
And have you looked at any robustness properties of the gains provided by those gains?
So when you're talking about that, you are looking at the disturbance to the system, right? And I haven't done much on that part, but I think, like what could be the disturbance? Because for the simple model, it's a model with mass property, it's constant height. So yeah, I don't know. I haven't looked into that, but it's a good question.
Is Ryan here? Okay, you can get started, set up. Any other questions? Okay. One more question.
Question, Kevin Green from Oregon State. Question is, when you transfer to your simulation capacity, do you see a breakdown as you get to even longer and longer step lengths or faster and faster speeds?
Yeah, you will have longer and longer step lengths because I'm keeping the step duration fixed. Yeah, you're absolutely
So
right.
how fast can you be able to push it before it breaks down?
Breaks down. I haven't even explored that. I think it depends on the step length and your step frequency. And at some point it will feel because the device is not capable.
Let's thank our speaker.